Please welcome Tim Ellison to the stage.
Okay, thank you very much. That's all I get. Thank you. Yeah, so my name's Tim Ellison. Welcome back after lunch. I hope you all enjoyed your lunch, and thank you for coming to this session. I work at IBM in Hursley in the UK, and Hursley is one of the sites that IBM uses for developing the Java implementation. So we've got a number of sites around the world working on the JIT compiler, working on the core VM, working on different parts of the class libraries, working on the tooling, all the service and support, and all the kind of stuff that goes along with implementing Java. And I guess it's my privilege today to stand up here and tell you about some of the work we're doing in the Java virtual machine to improve performance of Apache Spark. But of course, I represent a much bigger team behind me, which should take a lot of the credit for the work that I'm going to talk about today. Immediately before lunch, in this room, there was a talk by Tim Berglund about Spark and Cassandra. Did folks attend that talk? Okay, most people sort of followed through, so that's good. There'll be a little bit of overlap, because I'm going to go through again, just as a courtesy to the guys that weren't here, and talk about RDDs and that kind of stuff, so that we're all level set on the terminology that I'll use when we're talking about some of the implementation details. Any questions, feel free to put your hand up as we go along. I don't wear a wristwatch, so I'll try and keep on time. But if there are any sort of long questions or discussions that come out of that, I'm not going to rush off to the next session, so we can talk outside as well. So Apache Spark, as you will guess, is a project of the Apache Software Foundation. It actually came out of a project from University of California, Berkeley, their AMP Lab group. We're looking at this kind of next generation from the Hadoop MapReduce metaphors, and have built a whole natural, they call it kind of the natural successor to MapReduce. It's a very active project in big data. At the Apache Software Foundation, it's probably the most active project there, and there are a number of committers and active users all around the world who are deeply into this stuff. IBM has also made a pretty big bet on Apache Spark as being the platform on which we're building a lot of our analytic capabilities. And so for me and the team, as a VM implementer, it's in our interest to ensure that Apache Spark works as efficiently and effectively as possible on all different kinds of kit, but particularly on IBM kind of kit, of course, because that's going to be a foundation for all of the capabilities of the products that we have. Right? The next generation of products are going to have some level of self-reflection intelligence. We're producing lots of data in the middleware and in the end products, and the observation is, if you can reflect on that information and actually use that to improve the products themselves, then you get better products out of it, and you can solve new types of problems. So that's why Spark's important to us and to me in particular. And so just to do the quick introduction as to what Spark is for the folks that aren't that familiar with it, there's a mandatory block architecture diagram. There's a core layer in Spark, which is where things kind of all boil down to operations on the core capabilities. And built upon the core APIs are a set of higher level capabilities and functions. So core has got the basic MapReduce type capabilities, functional capabilities. And then built on that, there are a set of APIs that allow you to express your queries in SQL, for example, which map down into some of those core capabilities. There's also a streaming API for time-based data. So it'll discretize data as it comes in over a time series, and you'll be able to do operations on those. There's a whole machine learning library for much higher level operations. So if you're doing things looking for statistical operations, for example, there's a whole bunch of operations that are already defined and optimized to work on the core. And graph manipulation. So again, counting number of edges, nearest neighbor, all that kind of triangle counting. If you're into that kind of stuff, and that's the problem space that you need, the set of APIs which are optimized already and part of core. And then built around that, some of the newer concepts of data frames and machine learning pipelines, which I'm not kind of going to get into in this level of discussion. But then across the top, you'll see the different API languages which are supported by Spark. So people can approach Spark and program it in Scala, which Spark itself is primarily implemented in Scala, and so that's a very natural way to use it. But also there are a rich set of Java APIs which got all the same sort of capabilities. Or if you're doing an ad hoc analysis of your data, then you may choose to be using Python. So there are Python APIs, and of course the data scientists, a lot of the hardcore data scientists are guys that come from an R background, and so there are a set of R APIs as well into Spark. So that's how the programmers see Spark, that's how Spark manipulates it, and then the data that it manipulates can be held in a variety of formats. And Spark allows you to build bridges out into any format that you choose, but it comes with a whole bunch of bridges already available for Cassandra, as we heard about before lunch, and HDFS, and all sorts of popular data stores. So that's kind of the real big picture of what Spark is and how it breaks down. One of the advantages of Spark is that those different APIs all come through core, and they all operate on the same underlying principles of the data and the functions that you can apply to that data. So whilst I've mentioned that core is MapReduce, and you can write code as over there on the right-hand side box at the top that says I'm going to take a file and I'm going to do a map operation and then a reduce, etc. You can also take the same representation of the data and do an SQL operation on it. So you can actually express different parts of your application using these different levels of API. You can drop from a very high-level machine learning call all the way down to an individual rummage around through the data in the data set. And it's, I think this is one of the most powerful features of Spark, really, is that it allows people to operate on the same data at a variety of different levels with full interoperability between them. So you pick the right abstraction for the sort of problem that you're looking to solve. And then the power of Spark comes from the fact that it is going to distribute these operations out into the cluster. And so you can run it on a laptop, on a single machine, but you're going to get some real benefit on very large pieces of data by sending it out into an arbitrary cluster of machines. Now, they're organized using a master node, which is the thing which is running your application, and taking all of the API calls at the core level and starting to build a graph of what those operations will look like. Now, Spark works in a very lazy manner, meaning that those operations are just remembered as operations on the underlying collections until you actually ask for a result which causes them to be evaluated, at which point Spark will look back at the history of the operations to get to that point and then start to do some optimizations on it. So rather than sort of naively saying, okay, now it needs the answer, what it says is, how would I efficiently get this answer knowing that these are the transforms that the user has requested to get there? So there's already a level of sort of compiler theory that comes in here that says, I can start to rearrange some of these. If I start to narrow early, then perhaps I can do some of the more expensive operations after that narrowing and reduce the overall cost of the program. It can start to distribute some of those operations. It can recognize that there are dependencies between the various flows of transformations of the data and start to distribute those out into the cluster. And so in the cluster, you've got the master node, which is kind of figuring out these stages of the work that have to be done and distributing them out to worker nodes. And the worker nodes' role in life is to execute individual tasks. So they're receiving a copy of your application data. So if you're doing a map function, for example, obviously you need to know what the map is that's going to apply to each of the elements in there. And then it takes a copy of the data as well, and Spark is careful to ensure that the data is located close to the masters, the workers that are working on it. I just realized that I'd picked up what I thought was an apple juice at lunchtime. Turns out to be beer, but if I get more lucid as the talk goes on, you'll appreciate why. So that's how the application works. Now, the data that you operate on in Spark is called this resilient distributed data set. And as I say, Tim spoke a little bit about this before lunch. Conceptually, just think about the RDD as it's a massive collection that represents all of your data. So if you need to deal with a terabyte's worth of data, you can represent that as one DD, and if you really wanted to, you can iterate all the way through it. It's conceptually one very large hunk of data. The RDD itself can be backed by the original source of the data. So if you've got data coming in from some particular event stream or operation, or it's being pre-computed, it's the logs from your web servers, etc. They could be stored in HDFS, and RDD can represent that data as it lies on disk at that point. Or as you go through the operations and the transforms, as I say, it's lazily evaluated. So you'll do a map operation, you'll immediately get back a new RDD. RDDs are immutable, so you get a handle to a new RDD, and again, that eventually is backed by real data, but these intermediate RDDs then become, as kind of depicted in this diagram, they're derived from. They can remember their lineage to get to that particular point. Now, I've described the fact that they're a data set. Let's work backwards. They're distributed. So obviously, you're not going to bring your whole terabyte worth of data into memory simultaneously. So an RDD is partitioned into a number of partitions, and each of these partitions can be worked on independently from one another. And they're resilient because Spark will keep track of the data and where it is, and how you obtain that data, and it will start to cache some of the intermediate results. But if a worker were to disappear, then Spark still has the recipe for how you got to that particular RDD, and it can recompute it. So if you ever get under sort of pressure of memory, and you need to start discarding things from memory, or a worker disappears through some event, the machine goes down or whatever, this RDD intermediate state can be reconstructed, and that's why they're resilient distributed data sets. Just a little bit more about the background, and then I promise we'll get onto some VM stuff. When you're looking at the performance of Spark and looking to optimize that, then it becomes, you can boil it down to a couple of questions. So we've got all these we've got an RDD, a number of RDDs. They are split into partitions, and we've got a whole bunch of workers that want to work on the data in the RDDs. So the first thing that's going to limit my performance is how quickly can I get the data to the worker that needs to work on it. Okay? And then, once the worker has got that information, how quickly can they actually process the operations on it, and if necessary, cache that information so it can be reused in later stages. Does that make sense to folks? Now, when you're doing these operations, there are some operations which naturally lend themselves to parallelization. So, as I mentioned, Spark does optimizations of where the data is and how the data gets moved around within the cluster. And every worker in the cluster has got a copy of the application code, so it can equally execute on its local piece of data. But if you're doing what we call these narrow operations, such as map, so if you're taking a piece of data in your RDD and you're applying a function to it to produce a new value, that's something which can be done in parallel across all the different partitions in the RDD. And so on the left-hand side here, you can see that all of those things can be run in parallel. They're pipeline-able. Other operations, notably the reduce operations, that is, you're taking two values and you're combining them together to produce a single value, requires you to fetch two pieces of information. Now, you can also do part of that within a partition, but at some point, you're going to need some data from a different partition that's on a different node somewhere. So you're going to have to shuffle, i.e. take a partition from one node and bring it over to a different node. So how quickly can I shift the data around inside the cluster as well? It's going to be a very key part of what we do. So this is where the JVM comes in, right? One of the advantages of working at IBM is that I can pick up the phone and talk to the hardware designer guys and say, yeah, it would be really cool if we had this feature in hardware to enable this to happen, please. And likewise, I can phone up the guys that are working on Apache Spark application layer and say, if you wrote your code this way, we could optimize it way better. And so being that glue layer, our role in life is to get out of the way to ensure that whatever's been expressed at the Spark level is as efficient as possible in the hardware at the end of the day. So some of the things we're going to look at optimizing are JIT compiler enhancements, and writing code that's going to go through the JIT very nicely. Object serialization, again, is part of that storing the intermediate results. faster I/O networking storage, and offloading stuff to GPUs. And I realize I'm running long already, so this is going to have to go a bit quicker. Right, JIT enhancements. The first thing you do is profile your Spark application, figure out where the hot spots are and which bits need to be fixed. And when we did some profiling of Spark, we found that there was a JNI call in there which was showing up as a particularly hot area that you look into, and this is a snappy serializer that's got a JNI call that ultimately boils down to just doing a mem copy of some data between two different addresses. And this kind of makes your heart sink a little bit, because JNI is not a free call, all right? The fact that it's written as a native there, to many people would kind of assume that means there's some optimization going on beneath it. But actually, there's quite a lot of work required by the VM to set up the whole context of calling out from Java. We need to inform the GC that it's not allowed to move these objects anymore, that are getting passed out there. The JIT itself obviously doesn't know what's going to happen inside that JNI method. And so the arguments that you're passing into the JNI can't be pulled out and optimized in the compilation of the Java methods themselves. So the actual overhead of calling JNI calls can be quite significant, both in terms of the actual JNI overhead and the implications of the data flow analysis that the JIT is trying to do. So doing things like just a mem copy just aren't going to help that much at all. The other thing is that once you go out over JNI, even though the guys there were using get primitive array critical in an attempt to give the VM a hint that, you don't need to, when you get array primitive critical, then there's only limited operations you can do within that before you need to release it. And this is to say that you can let GC get a hint about that. In the IBM JVM implementation, we actually end up copying that memory as well. So there's going to be an overhead of copying data, as well as the whole point of data flow analysis not working so good. So the moral of this story is that we have to have judicious use of these JNIs. And for the purpose of this snappy, you may need to kind of hold your nose and implement using sunmisc unsafe to do the low-level operations, to copy some memory that can't be done through regular Java code. The other thing that we looked at was some optimizations for logging. And it was in the VM Summit earlier this week, where people were picking on logging as a particular, it was Martin Thompson's talk was picking on logging as a particular example of things that really can cause trouble. So here in Spark, they have a kind of a pattern that says that they're going to use this log info call. Laser pointer's not working so good, so hopefully you can see that in the second block down, log info. That's kind of a very typical way of calling it, and of course log info then is implemented, as you can see further up in the box above that, and does the first check to say, is the logging enabled? And if it is, then go ahead and do the logging. Otherwise, it's a no-op. We can actually do better than that using the JIT. We can actually switch it around a little bit and use a static class info logger in the places which we're going to want to do some logging. And then you don't have to, and then lazily initialize that class if you actually want to turn on logging. And the advantage of doing it that way around, rather than doing the test of the static, is that if you're testing the static, we have to go and have a look at it every time anyway, right? Because someone could have flipped it at any point. If you haven't defined that class yet, that class is not loaded, then when the JIT is compiling, it knows that class doesn't exist, and so it can just compile without any references to that class. And in that case, the info logger not null just means that that whole expression will disappear. And then we hook into the JITted code the event that says, when this class gets loaded, I need to go back and recompile this method over here. And that sort of things, we have to do that anyway for the devirtualization of a lot of methods. Judicious use of polymorphism. So there are, Spark has got lots of these polymorphic interfaces and a very high fan-in, right? There's lots of places that are calling onto them. So what we're seeing is lots of places that call, sort of, for want of a better expression, ambiguous methods. The external sorter insert all came up as a very hot area. It uses an iterator to drain the collection through, and using next and has next. And using these different iterators, you don't actually know at runtime which one we're going to end up using. So the JIT has to insert some option paths down there. And whilst we use profiling to figure out which ones are most common, the code may well end up defeating that optimization. The other problem that we saw is that of all the different subtypes of the iterator, they were implemented doing very similar things, but using different patterns, sort of somewhat gratuitously, the order in which they would do things. And again, that just doesn't help when JITting the code. So, looking for judicious use of the polymorphism there, I think would allow us to recognize the byte sequences, produce more efficient code, and lead to overall improvements in the performance. So once we started tweaking the JIT heuristics a little bit to take account of some of the ways we saw Spark being implemented, and Scala being implemented, of course, because Scala is sitting on top of. Then, over time, we saw the JIT kind of getting smarter and smarter. From between our Java 8 GA release and the latest release, it's about 1.35 times faster on the high bench performance benchmark. And that's kind of paying us some divvies in the performance compared to OpenJDK 8 here. So when you're looking at terror sorting information or page rank, then we're seeing some pretty interesting numbers there in terms of the boost in performance for running those benchmarks. There's still some work to do on that Bayes one. That's dropping below, but that's very JNI heavy, and I think we have some ideas about how to improve JNI for that. So that's kind of fundamental stuff. Once we, and that work continues, so we're always improving the JIT to run the code better. But then we started looking at what are the other things that we've got in our bag in terms of technology that we can bring to bear in this space. And one of the places we had a look at was replacing object serialization. Now, I mentioned kind of right near the beginning there that Spark will serialize intermediate results, or you'll take results and you'll store them persistently on disk. And we've done a whole bunch of work on serialization anyway, back in the days of the orb, which was serializing objects. So we thought, can we bring some of that knowledge to Spark? And Spark has got this convenient plugin architecture that allows you to write your own serializer. Now, they used to use regular Java serialization to begin with. I think it's the cryo serializer by default now. But could we get some performance by reducing the amount of time that the serializer spends introspecting the objects to break it down into its primitive types and all the reflection stuff? And also, can we reduce time by minimizing the size on disk of a serialized object so that it consumes less time in the I/O system? And so we looked at customizing the serializer so it would recognize a number of more of the types. So rather than having to, as I say, use a very generic reflection kind of mechanism, it would say, oh, here's a tuple, a Scala tuple, I kind of know that. I'm going to write out a specialized form of that with a tag on that I'll recognize on the way back in again. So we did that, and we did some sharing on the stream to try and reduce the size of the stream, which is fine. That gives you the ability to kind of put references in the stream to say, it's kind of like that object that I told you about before. It's not identical object, so don't link to it, but kind of create one of those and we'll be good. That's fine. You can get a bit unstuck with that because, as I mentioned, Spark will distribute work out into the cluster, and so what you don't want is dependencies between data that splits across the cluster. So if you've got one partition over here that says, I've got a reference to that data way over there, that's not going to be so good. So the various techniques we kind of had to play with that, including the actual implementation as well. So we played with making our serializer stack-based, so we could pop stack real quick, but then found that the RDDs can get really, really deep because of all these nested operations on RDDs, and so you've got to be able to switch then to a state machine to represent that. And after all this kind of evaluation and stuff, the conclusion, my conclusion was, it's not really worth the effort. You know, the current serializers are good enough that we can win a few percentage points at best, right? And I'm looking for something way better than that. So this was an experiment that didn't work so good. Faster I/O and networking. Faster I/O through networking and storage was another interesting area. So we've got some technologies in the IBM Java team that we can bring to bear on shifting data around. So we already have got some RDMA capabilities. And very briefly, imagine you've got the two machines in the blue and the yellow there. And when you're shifting data between them using sockets, then your data at the top little boxes here is either going to be in the Java heap, that's the buffer on the left-hand side, or it may be some combination of heap and direct byte buffers off heap there. But typically what happens is you go to make a socket call, it gets copied down into the OS TCP stack, then goes over the network interface card around the Ethernet switch and back up to the other side. And so there's lots of copying going on as those buffers get copied backwards and forwards between two different machines. And we need to avoid doing that. So, the other overhead is that because you're involving the OS, you've got to interrupt the kernel and tell it that you've got some work to do, please. And that, of course, then stops it running other pieces of work. Is that JVerbs? Question was it JVerbs? It's actually made apparent through different sets of APIs. So yes, JVerbs is one of them. The RDMA interaction is called verbs, and so we've got Java wrappers called JVerbs. But we've also done a plugin to the existing JavaNet socket APIs. So you can actually create a look-aside file that configures to say, if you're going between this address and this address, use RDMA. The two sides will actually. Now, obviously, there's some limitations there because you're expressing them as TCP sockets, but actually it's going over RDMA. But by and large, that's working very well. Yep.
What kind of network issues are happening in the Spark layers? I can understand that sometimes I do transfer the large logs of data. Is there some kind of broadcasting system between the network guy in the States and where the team are
Uh-huh. So, So the question is, what kind of networking is Spark doing? How much data is it sending? And the answer is various amounts. So it's organized around Netty as being the principal server for sending and receiving the data between it. The data that goes over that will be your application. So as you fire up the master node, it needs to send out a copy of your application code to the workers. So that's relatively small. That's jar files going over the wire. It's going to be sending partition data. So now we're getting into serious stuff, right? So if you're pointing workers at particular tasks, they evaluate them, they have an intermediate result, they now need to send that result off to somebody else. That requires serializing it, sending it over the wire, deserializing it on the other side for somebody to see it. And then they have distributed variables as well, which can be arbitrary objects. So it's hunks of data, but typically in serialized form for objects, the main part of it. And the real advantage of the RDMA comes both from the throughput, so that's the amount of data that you can shift, but also, and perhaps more importantly, the latency, the amount of time that you have to wait for that data to come. RDMA's got much better characteristics in terms of both of those things. That meant it was something that we were really interested in bringing to bear to the Spark workload. So we've tweaked Spark. I kind of said that that Spark is sat on top of Netty. You can actually just use regular NIO. I think that's been taken out in Spark 1.6. But they do all their I/O through Netty. And Netty itself then uses NIO to do the operations over the Java sockets. And so what we've done is we've plugged in different transports to the Netty capability. So because our RDMA implementation is not fully NIO enabled yet, it's using JavaNet socket, regular I/O stuff although NIO is coming. The first piece of work that we did was to write a plugin for Netty, which went over ordinary Java sockets, and then mapped those ordinary Java sockets to RDMA. And that saw some pretty good improvements straight out of the box. And then there's work underway at the moment to plug into Netty some JVerbs or some straight to RDMA capability for Netty. So once we do that, this is RDMA over socket capabilities. And if you're shuffling the data around, so again, this is where you're going to have to pick the benchmark appropriately. It's no good looking at one which is CPU bound. This is one where you're going to have to start shifting data between workers. Then, just by tweaking the Netty implementation to go over RDMA, we're starting to see 30% better response times and less CPU utilization because we're not interrupting the CPU all the time to let there's some data transfer. So that's a bit more of an interesting number. Other technology that we've got is Capi Flash. So this is a capability of the power architecture. Capi stands for this Coherent Accelerator Processor Interface, but everyone just calls it Capi. And it's a way of plugging onto the actual bus, so you get a coherent, meaning the memory is I was going to say synchronized, but it's coherent. Coherent between the main memory and what you're seeing in the flash space there, and you can address it as real memory. So whereas normally if you've serialized your object, you now need to store this cached value out somewhere because you can't maintain the entire partition or number of partitions in memory. What Spark does today is it sticks it out on the file system. And the path to get to the file system is kind of depicted by this little flow chart here. So you're talking about 13 microseconds there for total data preparation to get the data out. Whereas if you're using this Capi Flash capability, then we can collapse all that stuff down to a much shorter set of operations to get there. Now, this is an advantage of having this block I/O system, because we obviously run it with RAM disks and stuff, and it's going to the same type of flash at the end of it, but the overhead was in the file system implementation. And so once you switch to using this coherent block store, then you're not having to deal with the overhead of maintaining a file system on top of it and having to deal with directories and all that kind of stuff. You can just store blocks of data, and that's sufficient for what we need. We just need somewhere we can park it. These flash drives go up to, I think, 40 terabytes in power lock. So that gives us effective memory storage location outside of that. There's a couple of places where we need to tweak the Spark code to take full advantage of that. But you start to see the benefit of it when you are running more and more of your Spark tasks in memory. So the workers are in this logical cluster, but of course you can have multiple workers on an individual machine. And if you're in a cloud environment, you want to make sure that you can cram as many of these things into memory as possible. And so here we're able to reduce the amount of memory that we give to each individual worker and still see the same throughput for it. Okay, so that's reducing our cost of ownership on the cloud bill that we get at the end of the month. And so we were kind of graphing that to see how much Java heap memory we would be equivalent to. And the little kind of red dotted line here is just a case in point that on the blue line, which is when you're writing this cached data out to disk, you're getting a level of throughput in milliseconds that is matched by using 2 gigabyte Java heap when we were able to stick it out onto the Capi Flash. But if you really want to get, some good, sorry, yes, this question? Uh-huh.
First you say that you bypass the file system overhead.
Yeah.
And then we talked about this sort of IBM-specific hardware features.
Yep.
Are those sort of related, or can't you do this bypass file system on any hardware?
So the question is, can you do the file system bypass on any hardware? I'm only familiar with the IBM one, to be honest. I don't know if other folks are doing the block stores on bus block stores like the Capi Flash. So I'm not familiar with it if they are. I don't know if anybody else has got any experience on other. Fusion IO? I don't know the answer to that question, sorry. Right, the 3D point I think is one, yeah, I have heard discussion there. Coprocessors. So in our implementation of Java today, we already use graphics processing cards as part of the standard library implementation. So today, if you call arrays.sort with integers, longs, doubles, floats, and if the array that you're passing as a parameter is large enough to hit our heuristics in the class library space, then we'll already take that array, send it down to a GPU, and sort them there and bring them back. As you'll see from this graph here, the sort of the throughput that you get by doing that operation on GPUs is quite significantly different to what you get by doing it on the CPU. So the cutoff point here, I think it says 30,000 on this graph. I think the heuristic's actually in our Java 8 implementation of 20,000. So if you pass an array of 20,000 ints to arrays.sort on IBM Java, and you've got a GPU card enabled, then it will offload that down to the GPU, do the sort there, and bring the results back. And from an application perspective, it's just a call to array sort. It just sorts it that much faster. And once you start getting up into huge numbers, when you're sorting millions of elements, then you get a real payback. Also, this is a logarithmic scale here, so you'll see that there's a massive difference in the two implementations. That's kind of an explicit. That's because we have the ability to change the class library implementation to redirect it down to sorting on the GPU. But one of the other pieces of work that we do is to change the JIT compiler to recognize some of the expressions in the Stream API and to also compile those down to GPU code. Now, this comes with a whole bunch of different caveats. So obviously, if the data that you're operating over is object pointers back out into the heap, then we're not going to move that data down to GPU and start rearranging it because the pointers all get messed up. And we have to have various sort of pessimistic assumptions about when we copy the data. So there may be some unnecessary copying because we can't detect whether you've actually modified it or not in some particular instances. But with those caveats aside, the general flow is that we're looking through the application code, whether it's Spark or random application code, compiling that down to JIT form, and then running the heuristics on that and saying, does it make sense to offload this task out onto the GPU or not? So by way of an example here, and this kind of follows on from Brian's parallelization talk this morning, if folks were seeing that. Taking an int stream with a particular range here and calling the parallel function on it is the indication that there's no dependencies between these bits of data, and you can parallelize the operations. So we've got a parallel for each, and then within the loop there, it's kind of simple math operations. All right, so here we're not rummaging over objects and taking references through instance variables and that kind of stuff. So the JIT has compiled that loop. It's figured, this is a good candidate for sending to GPU because it fits all the criteria that we've got. And so the code that it emits is not CPU code, but it's GPU code, and then it branches down onto the GPU to invoke that particular kernel. And then you can see in the graphs here about what happens when you run that on a GPU-enabled host. There are 3 different bars for each matrix size that we measured here. The blue bar is when we have auto SIMD enabled. I've not really spoken about that, but that's an automatic parallelization on the GPU architecture. Allows you to take 128-bit register, fill it up with 4-byte integers, and then do the operations just in one cycle on that. The green line is just a parallel for each on the GPUs, and then the red line is what happens if you do the parallel for each. I beg your pardon, the other way around. The red line is a parallel for each on the CPU, and the green line is a parallel for each on the GPU. And so yeah, thank you. And so, yeah, there's a heuristic here where it makes sense to switch over from using the CPU to the GPU, and that gives us some nice implementation speed ups as well. Yep. Oops, let me just go back a moment. Was the blue line? That was still parallel, yeah. So then the question was, well, you know, that's great for moving these loops down, but if we really want to get a benefit, why don't we take some of the higher level algorithms and run those on the GPU as well? So the place where you get you know, the kick-ass performance is saying, I'm going to write a GPU kernel that can do some of those machine learning algorithms that are part of Spark's high-level APIs. So one of the, why does it do that? So one of the APIs in Spark, maybe it's the battery, I'll turn it off. APIs is for doing linear regression over a number of data points. And so the piece of work that was done here was to look at how fast we could do that linear regression over a large body of medical data. So there must be some time thing, you know, auto-advanced thing going on. I'm going to speak real quick. So the first phase is to ingest the data. So we've got lots of sources of information that tells you about the drug similarity information between various types of drugs, and then other bodies of information that tells you how those two types of chemicals interact with each other. And so the question was, can you build a linear regression model which which will describe the interaction between a very wide variety of drugs, and then use that model to very quickly predict what the interaction will be between two specific cases which you didn't know about previously. And so the use case here is that, you know, you walk into the doctor's surgery and he takes a look at your previous prescriptions and has an idea of what the new prescription should be for you, but needs to have some idea that it's not going to adversely react within your body and cause great problems. So sort of personalized medication type of operations. And so when we took that linear regression function, and there's an existing linear regression implementation for GPU, and we hooked it in at the Spark level, then that allows us to just offload the entire data down onto GPU, run it there, and bring it back. And so in this little dashboard here, the various phases of the application are shown as rows. And so the length of time it takes to read in the data was 40 seconds when run on the CPU only, and a very similar number when run with the CPU and GPU, because of course the GPU wasn't directly involved in that. And then crunching the data to build the model, that's where it was put down onto the GPU. So, you know, we were able to drop the performance from taking over 700 seconds on the CPU down to just 28 seconds on the GPU. And then things kind of flowed on from there. So, you know, that's where you, yeah, not too surprisingly, I guess, that's where you get the biggest bang for the buck is when you move some of these very high-level operations down onto the custom coprocessors. Yes, sir. Yeah, so the question is this still running in multi-core mode? The answer is yes, but each of these pieces of work is running on a particular mode. So one partition of the RDD that's going to be doing the linear regression on it would be running on the GPU. And so, you know, what we have at the moment is actually that we've put GPUs into all the different nodes on the cluster. But one of the interesting things to do is to try and teach Spark about some of the capabilities of nodes within the cluster. So whereas today I kind of mentioned that work gets moved out to where the data is, because often the overhead is moving the data around to different parts of the machine. It may be that you've got a low-powered machine in one part of the cluster and a very high-powered machine in a different part of the cluster. And, you know, if one of them's got a real bad GPU card in it, you may be willing to pay the overhead of moving the data over to that to run it on the GPU. And so building some more of those smarts into Spark to be more self-aware of what the compute capabilities are across the cluster is... Yeah, so the observation was you could build a GPU cluster. Yeah, I think that would be a discussion to have with the Spark community, I guess, as to whether they want to be implementing a lot of the Spark capabilities on GPU kernels. Yes? So the question was, does the Spark community welcome these changes, or are we forking Spark, or whatever? Some of the changes are made in the VM implementation itself. So obviously the things to do with the JIT, that doesn't really intersect with what's happening in the Spark community. And the things which are happening in hardware, likewise, right? So this is, IBM saying we're going to put a lot of work into ensuring that Spark runs well on our particular stack. Things where we've had to make any changes to Spark, so we did have to make some for endianness and for assumptions were made about the Java implementation, have been very readily accepted by the Spark community, with open arms. They want it to run in as many places as possible, and getting that kind of flexibility. Things like the GPU, this is kind of proof of concept at the moment. So there are some discussions with the community. I think there's a discussion to be had about where the line is to, well, this is kind of a separate project that runs alongside Spark as to part of a fundamental capability of Spark. But at the moment, it's, let all the different flowers bloom, and we'll see which ones actually get adopted within the community. So just to summarize what I've been talking about today, we, as a VM team, I guess we're focused on the runtime core performance capabilities. There are other parts of IBM that are working up in that machine learning and graphing libraries, but as a VM implementer, I want to try and get the bits and the bytes to go as fast as possible and do that in a way that's going to be super efficient for Spark. There are some pieces of advice that we can pass up through the community, as we already discussed. The community are very open to taking that, and that's good to see. So we need to kind of get the message out about some of those coding styles and ways in which people can do that. And I already mentioned that we're pushing these things out through the Java runtime and into the Spark community. Thank you for your attention. There's lots more stuff that we're doing here. So we're doing some sort of monitoring tools as well. So you can start tying together some of the events that you see with Spark with the events that we see in the VM to give you some real sort of feedback on that stuff and work around security. I haven't got time to talk about that, but I'd be delighted if you want to reach out and have that discussion at some point. So thank you very much for your attention.
We have a few minutes for questions. Any questions?
I'm wondering about this RDMA for the network optimization. Mm-hmm. Does that mean that you're sort of bypassing the TCP/IP protocol also, or?
Yes.
Okay.
So when you're running over, so the question was about, I guess it's recorded, you're on the mic already. Yes, as I said, there are different ways in which we interact with RDMA. So if you wanted to do native RDMA, then you use the verbs protocols, right? So RDMA through, there's the OFED stack that they use for interacting between machines that are connected via RDMA. And we've got some Java wrappers that will allow you to use the RDMA verbs. But we kind of realized, as I say, there's a lot of applications that are already out there which are based around the TCP/IP, JavaNet sockets, and Java NIO APIs in standard Java. And so we wanted an easy on-ramp for those guys to be able to get some of the benefits of RDMA. So it's a bit of an abomination, but we have, as I say, got a look-aside file that allows you to configure the runtime to say that when you're getting a TCP/IP call in through JavaNet socket, it's actually going to route it over RDMA. Now, you can set socket options through JavaNet socket that won't make any sense in the RDMA world. And so there are a bunch of caveats and limitations as to, if you depend upon some of those things, then your application will need tweaking for it. But we've actually had some very good results just by running it over that way.
Okay, that's all we have time for. Please give a hand for Tim.
Thank you.